Hi everybody, I'm Russell Spitzer. I am a software engineer at DataStax. I've been working with Spark since Spark 0.9, so I've been in a lot of bad situations with Spark where you get to those sharp edges and all of a sudden things stop working and you end up having to spend a lot of time debugging and tuning things. And especially since we work with Cassandra as well, we basically have two different systems that have all sorts of places where things might go wrong, and we want to make them work together well. So in this talk, I'm basically going to go over a lot of the more common symptoms of things and the patterns I see that people implement that usually cause those things to happen. So for example, we're going to look at those deadly out-of-memory errors, things like RPC failures, just the generic, oh no, it's slow right now, we need to do something about that. And we're going to do that through a series of code examples. So let's start with something I see most common in out-of-memory errors, slow code, and RPC failures. And that's something that looks a little like this. We'll see code, and somewhere nested within that big example of code, we'll see a collect, some sort of work done, and then a parallelize. So this is an RDD example, but the same thing can happen in data frames and data sets. And basically, the problem here is that we are moving our information to and from the cluster over and over again. Instead of doing something like this, where we're moving everything back and forth, we really want to keep as much of our work on the cluster as possible. So usually the replacement for this is something like just doing 2 maps in a row. And sometimes it isn't evident in your own code where you should be doing this, but basically you never want to see a pattern of going collect, parallelize, collect, parallelize, collect, parallelize, especially not in a for loop. So why don't we want to do this? Because collecting sounds pretty fun, and parallelizing is why we want to use Spark. So why don't we want to have this kind of loop? Well, we can kind of think about it like this. First reason is we're using Spark for a reason, and that reason is that we have a distributed system. We have a cluster with lots and lots of machines. And we want to use all of those machines. We want to use all of those resources. So on one hand, we do have our driver JVM. That's where all of our code that after we've run collect, it's going to run. And that's got some good pro points. It's dependable. It's easy to work with. It's very easy to understand and debug because there's only one of them. But the problem is that there's only one of these JVMs, and it's not very big. On the other hand, we have our cluster, which is the entire reason we're using Spark in the first place. So let's not do any work on the tiny thing and do lots of work on the big thing, because not only are we going to have problems moving data that fit on the cluster back, the cluster has many, many JVMs, and each of them has their own heap and can store a huge amount of data because each of them is only holding part of it. When we run collect, we try to take all of that memory and put it into the same JVM, one JVM, and that usually leads to out-of-memory exceptions. So that's one reason why we don't want to have these collect parallelize loops. We want to keep everything where all of our work can be done and not on our tiny little JVM. So another reason is that every time we do this movement of data between our driver JVM and our clusters, we're actually spending an extremely large amount of time. So this is a pretty old slide from a talk that Jim Gray gave, and basically showing that there's orders of magnitude difference between different types of moving data around. Some types of data, moving things around within the same machine are rather fast or relatively fast. But doing things between things that are very far away, for example, between disk I/O on a different machine somewhere else and your current machine are going to be orders of magnitude slower. So if at all possible, we want to minimize movement of data between machines. And when we do a collect and parallelize, we're actually forcing movement of data between machines. And sometimes we don't even need to do that. And the last reason that I would warn against this, even if we're not moving a huge amount of data in our parallelize collect loop, is that the way parallelize works is that it sends data in task metadata. So this might sound a little confusing, but basically when you say parallelize some collection and you want to send it out to your cluster, what Spark has to do is it has to break that collection down into pieces and then send those individual pieces to the cluster as pieces of the RDD's metadata. So when it does this, there is an inherent limitation, and that is we're breaking up a list into slices of that list, which means the minimal element that can be in one partition, one Spark partition, is one element from our list, which means that we can never break any elements down into sub-elements. So if we have a single element that's really large, so for example, I'm just running a little example here where we're making a single element treasure, and treasure is very large. Treasure is over 100 kilobytes. We put it in a sequence and we parallelize that sequence. We end up with a single task that has that entire element inside of it. So this means that if this element grows over time, if we're in some kind of collect for each loop where we perhaps do some sort of processing, get some kind of result, move it back to the driver, and then try to send it back out to the cluster again in a loop, and that state grows over time, we'll eventually hit an RPC limit and not actually be able to accomplish this. So this is really just not the way you want to move things back and forth. So my main point for this example is that when we're working with Spark, we want to keep the work distributed. So every single time we see something like a collect and parallelize, we should think to ourselves, why are we doing that? Why are we taking the data back and then pushing it forwards again? If at all possible, keep all of the work on the cluster by keeping those RDD map operations not broken up by a collect parallelize loop. And as a bonus, if at all possible, start out with your data parallelized. So I've seen a lot of applications where we start out by reading something and then parallelizing that collection to Spark. But this applies for all collections that are parallelized. So for example, reading a file and then parallelizing it, reading a file locally and then parallelizing it is going to move data in the exact same way. It's going to take all of those strings and then send them in RDD task metadata. So if at all possible, start out distributed. Have your data inside of Cassandra. Have your data in HDFS, your data in S3, in some way where Spark is not going to have to do a whole lot of heavy lifting inside of the scheduling portion of the code. So that was kind of a generic example of something that you don't want to do in Spark. A more specific example is something with data frames. So here is an example that I see a lot as well. So this is where predicate pushdowns end up failing when you've run some kind of Spark SQL request. So in this example, we're selecting from a table escapes. We're using a specific predicate here where time equals 11/27/1977. And perhaps we're using this on a source like Cassandra where we expect there to be some kind of predicate pushdown here. Maybe time is a partition key in Cassandra. And for those of you familiar with Cassandra, when we do a where request and specify the partition key explicitly, we expect to pull out a single row. We don't expect to do a table scan and to pull every single row out of the database. We should be able to go exactly to the machine where that data is located and pull that row in isolation. But you'll find out that if you do this sort of request, just as it is, you won't actually get any predicate pushdowns. And the reason behind this has to do with the type of the literal in the string that we've written here. And to explain why this is a problem and why we need to do explicit literal typecasting here, I'm going to just do a quick walkthrough of how Catalyst works. So Catalyst is definitely a black box to a lot of people. I mean, but really what you need to understand is that we take an SQL request or something written in the DataFrame API. We run it through a whole bunch of awesome code, and out comes distributed work. So SQL in, distributed work out. What it's actually doing inside of that black box is first it makes a logical plan, and the logical plan describes the what of what is going to go on in this query. It's describing, do I need to get information? I need to get it from something called test escapes. I need to apply some sort of filter to it, and I need to get all of the columns out of that. So that's basically what the logical plan says. These are all the things that we expect to happen in this query. Then there's a transformation done by the optimizer which changes this logical plan into a physical plan. And the physical plan tells us exactly how that's going to occur. It tells us what code is actually going to be run to make that logical plan happen. So in this case, this is the physical plan for this query. we'll see at the bottom there we have a scan from Cassandra. And above there we have a filter operation, which is being done in Spark. So this tells us all the information about what code will actually get run when this query is executed. And one of the key things we notice here is that that filter is separate from Cassandra. It's not happening inside of the Cassandra node. It's happening as a completely separate Spark operation here. So why is this happening? Why is that predicate not ending up inside of the scan? So as I said before, this is all basically tied to the type matching system. So Catalyst, when it sees this, this predicate here, this comparing the column time 5 to that string literal, it knows that it needs to make a type match. So it's going to first take a look at that. And it's like, you know what? This looks a lot like a string. And I have to compare this to time number 5. But time number 5 is a date. So one of these is a string, and one of these is a date. But I can't compare strings to dates. I need to make them both either strings or both dates. So Catalyst makes a great decision and decides that they'll both be strings. So unfortunately for us, this means that it needs to apply a cast to the column. So it's going to cast our date column from Cassandra into a string. When it does this, we now have a function applied to the column, and functions cannot be pushed down to data sources. Which means that since there is something applied to this column before the expression is, the filter is applied, we can't actually push it to Cassandra. So the way we get around this is we let Catalyst know ahead of time that that number, 1977-11-27, is actually a date and not a string. So it doesn't have to worry about making this kind of functional casting. So instead of doing the previous request, we do a request that looks like this. We select star from test escapes, where the time is equal to our literal, but we're making sure our literal now is expressed as a date to Catalyst. Now this time, Catalyst is going to think about it. We're going to go back to our magical black box. It's going to generate a logical plan. Now, we wouldn't expect this to be any different, and this is exactly the same logical plan as we saw before. We're comparing some column named time to some literal called 1977-11-27. But what you don't see here under the hood is that the optimizer now sees these two comparisons, this comparison and the filter, as being of the same type. So when it does that, we get a completely different physical plan. Our physical plan here has one single node. And the two important things to notice about here is, one, that of course there is one single node, and that inside of our Cassandra source relation, we now have a pushed filters item that wasn't there before. So this lets us see that when it's going to perform this query, it believes that Cassandra is going to be able to handle this kind of predicate, the predicate equal to time and then our date. The little star there on the side lets us know that Spark believes that Cassandra source relation can handle this predicate entirely on its own. It needs no additional help. So when Spark is planning out the rest of this logical plan, it knows it doesn't have to do any kind of filters because it knows that that filter is already being taken care of. So if we do this, we do get a successful pushdown. And we will successfully get our data out of Cassandra with a single row read instead of a full table scan. OK. So this is one way of kind of getting around some issues with Catalyst. But another issue that I see a lot of people run into is when they're working with their own specialized code to try to read from Cassandra or write to some kind of system or read from some kind of system that has a huge I/O penalty but not a lot of CPU usage. And usually that looks a little something like this. We have some kind of RDD or a data frame or a data set. And to that we apply a UDF that takes a lot of time I/O-wise, but doesn't take a lot of CPU time. And this is where we need to talk a little bit about how concurrency in Spark actually works. So concurrency in Spark is a pretty easy model. We have an iterator, and we take items off of that iterator one at a time. We can't have more than one item taken from the iterator at a time, and it's always pull requests. So the last action in your chain of Spark actions is going to pull elements one at a time to actually execute your code. Now, the problem with this is that we do only have one element processed at a time. So if our operation here is really slow but not CPU intensive, we don't end up using all the resources on our machine. The way that Spark achieves concurrency, which you probably have seen in a lot of other talks at the conference so far, is it uses multiple cores. Now, each core that Spark is running has its very own iterator that it's pulling from. So we basically end up with as many elements being processed simultaneously as we have Spark cores. So this means that the only way to increase our parallelism on this Spark level, at the Spark scheduling level, is to increase the number of cores that our application has. But sometimes that's not the best way to increase parallelism. So like I said, what if we have an operation that's really slow, it's I/O limited, but then we follow up with something that's very fast that we can do very quickly? So we don't want to increase our parallelism for the second step, but we really want to increase our parallelism for the first step. We want to make sure that we can get to the part that we have the right parallelism for without waiting too much. So there's a couple ways to get around this. The first is you can just operate on groups of items. Now, if we just group our iterator up and we write a function that works on multiple items at a time in parallel, then this will work to let us add additional parallelism to this stage of our computation. But the problem is this will slow down to the slowest element of the group, because we have to wait for everything within that group to complete before we move on to a new group of items. Another thing you can do is kind of work with futures, but if you're not using a for each at the end of your operation, you can't be sure that you will still only draw one future at a time. If you're using a for each, you basically then can't check whether or not your future is actually complete. So what we do in the Spark Cassandra connector, and you can check inside of the Spark Cassandra connector for examples of this code and how it works, is we have a sliding iterator that takes futures. So basically, our plan is that we're going to try to start our slow operation, which in our case is pulling records from Cassandra. We know we can do this at a much higher parallelism than the number of cores that we're currently using. And instead of just taking one future at a time, we group our futures together into a set of some buffer. So we pull a certain number of futures off of our queue to do requests. And then we change that into a sliding window where as we complete one group of futures, or as one group of futures is pulled off of the queue, we automatically backfill in a new group of futures. So as we're processing our data, we're constantly adding a new set of futures to be analyzed. We then flatten that out and then change that back into an iterator of the items that we're actually expecting using a get operation. So basically, this puts a tiny buffer of async operations in the middle of our Spark chain of commands. So instead of waiting for every single request to happen in serial, we have multiple requests always going at a time. We still ensure that we get the same ordering of requests, but we can take advantage of the fact that Cassandra can handle a much higher parallelism than Spark would originally put on top of it. So that is my generic how we can get around some concurrency problems in Spark. But the next kind of thing I want to talk about is an optimization that I see happen a little too prematurely too often. And that's when we see people doing a lot of RDD caching, mapping, or something like this, where we're caching our data all the time as we move through a dependency tree, or we're working with tables or things like that. And my big advice for this, if you take away nothing else, is let's not cache unless we reuse that data. So caching is not a free operation. It kind of seems like it's a good fallback and a good thing to save you time. But let's just take a little example that I ran on my laptop. So obviously, your mileage may vary. And with different kinds of code and different kinds of operations, you'll see different performance. But here we have an example where up at the top, we're going to read from Cassandra. And down at the bottom, we're going to read from Cassandra, but we're going to cache the result. The little map R to R right there is just to make sure we don't do a count predicate, count pushdown to Cassandra, because we want to make sure that we're actually counting our elements and not doing a count request on Cassandra itself. If we check out the times of these on my laptop, these two requests have extremely different times. When we run our operation with a cache, it takes almost twice as long as if we had done the read just straight up and counted our elements. And there's a lot of reasons behind this, but first let's just kind of use some basic math to figure out when then does it actually make sense to cache our data. So let's just do a little math here. Let's assume that our caching costs C seconds, our normal run costs R seconds, and failures happen at a rate of F. And I'm just going to do a first order kind of check on this, which would be that the caching is helping us out if the amount of time it takes to run after a failure plus the chance at which a failure happens is greater than the time that it took to cache and then run, then caching helps us out in case of failures. So again, this is considering we aren't reusing our data at all. We're just caching in case that read failed or that shuffle failed or that previous really expensive operation failed. So with the numbers, well, we can do a little algebra to toss that around. We can find out then that in this particular example, this caching was only worth it if 0.6 is greater than our failure rate, which means that we would need to fail more than 60% of the time to make it not worthwhile to just reread the entire data set. So in this kind of thing, it makes a lot of sense to look at the actual application we're writing and figure out, does it help us? Are we really saving that much time by avoiding a rerun of the previous stage? So for some things, for some very large shuffles, this is definitely true. For some very large reads, this is definitely true. But not for every single operation, which means that for a lot of times when you're doing this kind of caching, you probably end up increasing the cost of running for the average case. So why is caching so expensive? So let's think about, for a second, what actually happens when we cache. We basically have put a barrier where we need to take all of the information that's coming out of whatever came before, serialize it all at once, and make sure that we have a place to store it. And sometimes this means we even have to move things to disk if we're caching at a disk level as well. So we're basically spending a lot of time to hold all of our data at once, to serialize it all into a different form, and we might have expensive disk access. So that means we should really not be caching unless we're in a situation where our pre-cache computation is extremely expensive or we're reusing the data. So this is just a general thing to look at in your own applications. Look at all the places in which you're caching and ask yourself, is this really a place where things fail very often? Or am I doing this just because I'm worried about failure, but failure is not a very common occurrence? So those are my basic tips that I think most people should be looking out for when they're going over their applications. So let's just kind of go over that again. So we really want to make sure that when we are doing our work, we keep all of our work distributed. We want to make sure that when we're specifying things to Spark SQL, to the type system, we make sure that we explicitly note those types down so that when we are talking to a data source that supports predicate pushdown, those predicates actually make it all the way to the data source. We want to make sure that when we have the ability to do concurrent actions, where concurrency for our particular piece of code should be much greater than the Spark concurrency that's already provided, we want to make sure that that is done with some kind of futures or grouping or some kind of action like that. And of course, lastly, we want to make sure that we're caching only when we reuse our data. So these are my general tips to try to avoid some problems in your kind of applications when you're writing code, for working with Spark, for working with Cassandra, to end up with the most efficient applications you can. So before I get to questions, I just want to let everyone know that we just released DataStax Enterprise 6, which has new versions of the Spark Cassandra connector with all new exciting kinds of optimizations and things like that. And of course, if you want to ask me any questions, I'd be glad to answer them. And feel free to visit us at DataStax Academy, where we have a Slack channel where you are free to come and ask questions about Spark and Cassandra and analytics in general. So thank you very much.
Thank you very much. Give a big warm welcome. Do we have any questions? We got about 5 minutes. Remember, there is a Birds of Feather session, Apache Spark and Spark UTF around lunchtime. Make sure you attend those if you want to ruffle some feathers. But if you have any questions for Russell, please. All right, you guys are hungry, I suppose. Go ahead. Thank you.